So, welcome everyone to the 2026 Langtangen seminar. We're very happy to have you all back with us this year and today. So, for our first seminar, we are joined by Francesco Regazzoni, who is an associate professor in numerical analysis at Politecnico di Milano. When Marie and I were thinking about who to ask or who to invite this year in our seminar, we thought about some, let's say, younger faces or up and coming stars in their own respective areas. And so it was easy to pick Francesco, whose work bridges the gap between rigorous numerical PDEs and modern scientific machine learning, as well as whole heart simulation. So he kind of is touching on real applications and classical numerical analysis and sort of the future of computational mathematics. So we're very excited to have him with us today. And Francesco is a European Mathematical Society Young Academy member. He won, was this the Gruppo 2003 AI Prize, if I'm reading that correctly? Yeah, and so beyond that, I don't want to take up any more time. So Francesco, the floor is yours. One more thing, sorry. If anyone has any questions, please write them in the chat and then Marie will field them later on.
Okay, great. Thank you very much. Thank you very much for the opportunity of giving this presentation, and thank you for the introduction. So first of all, let me mention that what I'm going to present today is the result of the work of many people that you can see listed on this slide. So today I will talk about learning across shapes. So non-intrusive mesh-free surrogate models via shape-informed operator learning. Let me start with a slide with the motivations behind this work. So let's consider what is the traditional modeling and simulation approach, for instance, in biomedicine. So what we typically do is that we start from images, we segment them, we generate a mesh, and then we exploit the knowledge encoded into mathematical models to deliver, to perform numerical simulations and to have results that can be useful in applications. But in this pipeline, what are the main bottlenecks? One is in the pre-processing steps, including meshing, that is very often time-consuming and difficult to make automatic. And second, the computational costs. We know that very often computational costs are prohibitive for applications. For instance, if you consider this cardiac electromechanical simulation, it took 4 hours on a supercomputer with 1,000 cores, with an estimated cost of nearly 2,000 euros in electric consumptions and also non-negligible pollution. So you immediately realize that this kind of exploitation of computational models is not sustainable, both for their computational times and also their cost. And so what we are trying to do is to exploit operator learning as a way to build surrogate models that can replace these high-fidelity solvers. So what is a surrogate model? So to construct a surrogate model, first of all, we need a physics-based model that in abstract terms can be seen as a map from some input. An input can be the set of parameters, the shape of the domain or functions, and some output, for instance, scalars or functions. Then we need a high-fidelity solver that is a solver based on classical numerical analysis, so for instance, finite elements. And then what we do is that we sample the space of inputs, we collect the corresponding outputs, which form the so-called training set. And then we select a hypothesis space that is a subset of all the possible functions mapping these inputs to the outputs. And then we look for the model belonging to this hypothesis space that minimizes the discrepancy between the predictions of the surrogate model and the results of the high-fidelity solver. Solving this minimization problem is called training, and the result is a surrogate model. That is a model that is typically approximate, so we have accuracies that very often ranges between 10 to the minus 2 and 10 to the minus 3 or relative error, but which is much faster. So we typically go from hours of computations to seconds or even milliseconds. And so the first question is it worth to construct a surrogate model? Well, actually, it's not always worth, but at least it is in two cases. One is that is when we need a real-time solution. So, for instance, if you need to assist the surgery during surgical operations, that you cannot wait hours for results. So, you need real-time solutions. Or second, when we need to query several times our model. So suppose that we need to do n query evaluation of the map from the data to solutions, then using a surrogate model requires this computational time. So we have an offline phase where we need, first of all, to generate the training samples, then we need to train the model, and then we need to query the surrogate model. Instead, by using a high fidelity solver, then the computational time is simply the number of queries times the number required, sometimes the computational time required by the high fidelity solver. And a trivial consequence is that if we want a surrogate model to be convenient with respect to the high fidelity one, we need the number of training samples be much smaller than the number of queries. And this, I think, is very often overlooked in many works. And here the main take-home message is that the surrogate model must be able to generalize well for unseen inputs, even when trained with a small number of training samples. So here the most challenging part when developing surrogate models is to generalize well when you have a small number of training samples. And the situation when this is particularly challenging is when the shape of the domain changes. So when we address shape-dependent operator learning. So the point is that most operator learning methods are designed to work on a fixed domain, but in many situations the domain can change. And so the key question is how can we generalize in a zero-shot manner to domains that we have never seen before? So the standard approach is been based on the idea of deformation of a predetermined mesh. So we have, for instance, preform deformation, methods based on radar basis functions or statistical shape models. But these methods have significant limitations. So first of all, in case we have large geometrical variations, then we can have distortions of the elements that can lead to ill conditioning. Or when we even have variations in the topology of the domain, then it's not possible to deform a mesh to account for topological variations. And very often the mesh is not even given, and so we need flexibility in the way how we represent the geometry. So in the end, we need meshless methods that are capable of flexibly handling different kind of parameterization of the geometry. For instance, we would like to handle geometries represented as point clouds. And with this in mind, we developed a method that we call USNets, Universal Solution Manifold Networks, that are neural networks that are able to learn the solution manifold of a PDE in a universal way with respect to the domain. So this is the general setting. So we have a full order model that is some PDE that is defined by means of differential operator. To stress the dependence on both the physical parameters and the domain, we employ this notation. So how is the architecture of our method? So first of all, we base everything on a neural field that is a neural network that takes the physical coordinate as an input and outputs an approximation of the solution in that point. So instead of outputting the full solution evaluated on a grid-based representation, we query independently the model for each point where we need to know the solution. So we exploit so-called neural fields. Then we condition a neural network on the physical parameters. And finally, in order to account for the shape dependency, we condition a network on the so-called shape code. The shape code is a finite dimensional encoding of the domain. So we will need to define the so-called domain encoding function. That is a function that, given a domain that is a subset of RD, obtains the shape code that is a latent code with a small number of parameters. So later I will give you some ideas on how we can define these shape encoding functions. And then we will simply train our model in a supervised training way, so by minimizing the discrepancy between predictions and data. And in order to better generalize from one domain to another, besides providing a shape encoding function, we also pre-process the coordinates by means of some positional encoding techniques that typically maps all the domains into a reference domain by using the so-called universal coordinates. And as I will show you, this allows to better generalize from one domain to the other. So now I address the question, how can we define a shape encoding function? So how can we associate a finite dimensional code to an infinite dimensional object that is a domain? So it depends on the use case. So for instance, very often we have parameterized domain, for instance, in industrial design. And so in this case, we will just use the parameters. In some other cases, we have some landmarks, so coordinates of key points. This is very often the case in biomedicine. Or we can exploit the statistical shape models. So the idea is that we find a point-to-point correspondence between different domains. Then we perform a PCA analysis over the coordinates, and then we truncate it and we take the first n principal directions. Or we can even think of learning a way to define a shape encoding, and this is what I'm going to address now. So one approach that we proposed is what we call the ADSVFD, that is autodecoded stationary vector field diffeomorphism. So here the idea is that we start from a template geometry, and we learn how to map this template geometry into any given target geometry. And this can be done by means of a neural ODE, that is an ordinary differential equation where the right-hand side is a neural network. So this is a velocity field that transports any coordinate of the template geometry into the corresponding coordinate of the target geometry. So by letting this pseudo-time evolve, we can continuously deform the template geometry into the target geometry. So in this way, we can describe a single geometry, and to pass from a single geometry to multiple geometries, we condition this neural network by means of a latent code Z that is associated with each geometry. And the nice feature of this approach is that we can reverse time, and by simply changing the sign on the right-hand side, we can instead move toward the target geometry to the template geometry. So this transformation is trivial invertible. And how do we train this model? Well, the idea is that at training time, we associate to each training geometry an unknown latent code from Z1 to Zn, and we simultaneously train the weights of the model and the shape code associated to each training geometry. So this framework is called autodecoder framework. And in the last function, we put both the forward approximation and the backward approximation because we have the invertibility of the map. But how can we find a shape code associated with the geometry that we have never seen before, since we don't have any encoder? Well, the idea is very simple. Suppose that we are given a new geometry. We will look for the shape code such that if inputted into the shape model, will output a geometry that is as close as possible to the geometry that we have. So in other terms, we will solve the same minimization problem that we have during the training, but now we don't minimize with respect to the parameters of the model, so the model is freezed. We only minimize with respect to the shape code. So this is a low-dimensional optimization problem that can be solved in a very small computational time, so very often just seconds. And in this way, we can associate a shape code to each geometry. So we apply this idea to a data set of 20 healthy aortic anatomies, and we got a latent space that is well behaved. And so how can we say that? Well, by two considerations. The first one is that if we take two geometries and we perform an interpolation in the latent space and then we decode them back into the physical space, we have a smooth transition between the two geometries, both by using linear interpolation and SLERP spherical linear interpolation. And second, if we randomly sample in the latent space with the code, we can perform generative AI and generate synthetic samples that are realistic. However, there is a drawback in this approach, that is, this does not allow for topology changes, since if the topology changes, we cannot define a diffeomorphism from a template geometry to an arbitrary geometry. And so this led us to explore an alternative approach that is instead based on representing a geometry by means of the associated sign distance function. That is a function whose absolute value is the distance from the boundary and where the sign is negative outside and positive inside. So again, we can represent the sign distance function by means of a neural field. That is a neural vector that takes the physical coordinate and outputs the value of the sign distance function. And we can condition this model on some latent code that is associated to its geometry. So to train it, we exploit again an autodecoder strategy. So at training time, we associate a shape code to each geometry, and we simultaneously train for these shape codes and for the parameters of the model. And at testing time, given a new geometry, we will simply look for the shape code such that if inputted into the shape model, this will output a sine distance function that is as close as possible to the one associated with the geometry at hand. And this inference problem, so this minimization problem, defines the domain encoding function. So evaluating the shape codes consists in solving this minimization problem that is, however, very lightweight because we are minimizing in a small dimensional space. So now I'm going to show you a benchmark test case. So we would like to predict the blood flow in a bifurcating domain with the presence of stenosis that, as you can imagine, vary dramatically the blood flow. So first of all, we define some universal coordinate systems by solving two Laplace problems, where by putting in a wise way boundary conditions, we can define a top-down coordinate and a left-right coordinate. Then to encode the shape, first of all, we consider landmarks, that is the coordinates of these points, and we consider two situations, one with 26 landmarks, so a quite accurate description of the geometry, and the second with only the 6 orange points, because we would like to stress test our method and to see how it performs with a poor representation of the geometry. And finally, we consider a goal-oriented loss function where we fit both the velocity vector and also a smoothed version of the direction, because we would like also to fit what happens when the velocity magnitude is small. And these are the results. You can see pairs of finite element simulation and neural network predictions in geometries that were not considered in the training set. And you can see that by using 6 landmarks, we can get accuracies that are comparable with the case with 26 landmarks, so we can generalize rather well. And you can see that by using universal coordinates, so the orange box plots, we can always increase by some amount the accuracy. And to understand why universal coordinate helps, we can look at this situation. So the key point is that the domain encoding function is never injective. So since this is low dimensional, we will always have two geometries sharing the same shape code but being different. And this is something that is unavoidable. But what happens is that if we have these two geometries, the surrogate at a given physical coordinate will always output the same result, which is of course not the case. Instead, by using universal coordinates, we can have an encoding of the domain that allows to better capture what happens, especially close to the boundary. So in this way, we can generalize better from one geometry to another. What happens instead by using learned shapecodes? So shapecodes learned by means of the deep SDF architecture. So you can see that by increasing the dimension of the latent codes, we can get more and more accurate results. And the accuracy saturates when we hit 11. And by the way, 11 is exactly the number of parameters that we used to generate the synthetic geometries. So we somehow were able to extract a parameterization that is equivalent to the exact ones. And here we compare the accuracy that we can get with learned shape codes compared with manually extracting landmarks, and we can see that we can outperform the accuracy that we can have with manually extracting landmarks. And this is instead a different test case. So a perforated plate that where we apply traction loads. These are elastic, and we would like to predict the deformation field. And here the test case is interesting because we also have variation in topology because we change the number of holes. And we can also benchmark the results with the solutions that we can have by providing the extra parameterization, because here we have an extra parameterization given by the position and the radius of the holes. And you can see that we can get an accuracy that is almost equivalent to the one with an extra parameterization. So this validates the goodness of the encoding function that we can leverage with this method. And finally, I'm going to show you a real-life application of this methodology to the field of cardiac mechanics. So we consider this problem. We have a left ventricle, and we consider a passive inflation of the left ventricle. So we consider quasi-static equations of elasticity with an anisotropical Zapfel-Ogden constitutive equation that is a highly nonlinear constitutive law. And this solution typically features large deformations and also cross-sectional twisting, which makes this particularly challenging. And here the challenge is to predict the equilibrium deformation field for geometries that we have never seen before, depending on the endocardial pressure and on the tissue stiffness. So we employed a dataset comprising 44 left ventricular geometries, obtaining from CT scans of 2 cohorts of both pathological and healthy patients taken by publicly available cohorts. And we immediately faced one issue, that is data scarcity, because we were able to find online only 44 geometries. That, as you can imagine, is not a large number if you would like to learn complex problems such as nonlinear elasticity. So at first we tried to reduce the variability of anatomies by factorizing out some rigid body degrees of freedom. So first of all, we addressed translation, and since the physical problem is translation invariant, we simply centered all the geometries because without loss of generality, this is something that we can always do. Then also rotation can be factorized out because the physical problem is rotation invariant, so we can align all the geometries as I will show later. And what about instead the scale transformation? Well, unfortunately, the physical problem is not scale invariant, but still we can separate the contribution between shape and size by performing a per sample normalization and then keeping track of the scale coefficients into the physical problem and into the physical surrogate. And later I will show you how. But first of all, let me show you how we factorize out the rotations. So first of all, we align the basal plane by performing PCA analysis of the points belonging to the surface and by aligning the center line with the z-axis. And then we also remove the last degrees of freedom, that is the rotation around the center line of the ventricle, by taking the centroid of the right ventricle points and putting it into the axis y equal 0. And you can see on the bottom, and in this way we can well align all the geometries. And then how can we factorize out the scale? Well, the idea is that we take all the geometries and we normalize them into the unit cube. In this case, we can focus just on the shape and not on the scale. So we train a shape model on this normalized space. And finally, we append the 3 coefficients that allows to inform about the size of the domain to the learned shape code. So in the end, the shape code will be split in 2 parts. The first one accounts for the size, and the second accounts for the shape, regardless the size. And so overall, in this way, we can reduce the complexity of what the shape model needs to learn by factorizing out all these rigid body degrees of freedom and also uniform scaling, but still preserving the size information as an explicit parameter that can be used by the surrogate model. So how do we perform training? So we take all the geometries, we sample randomly in the space, in the Euclidean space, in a more fine way close to the surfaces of the geometry in order to have a more accurate representation. Then we randomly sample shape codes associated with all the geometries, and then we train the shape model by backpropagating simultaneously to the parameters of the neural network and also to the shape codes. And the loss function includes the data fidelity term, that is the mismatch between sign distance function predictions and the ground truth sign distance function. Then we have a prior term that penalizes the Euclidean norm of the shape codes, because here we're imposing a Gaussian prior. And finally, also a regularization term that penalizes the Lipschitz constant of the shape model. Here, the idea is that we would like to have a regular map between the shape code and the sign distance function, because this will promote regularity of the latent space, and this will help the inference problem. So how does inference happen? So here we represent geometries in a very flexible way. So going towards application, we imagine that we just have a point cloud of points belonging to the surface of the geometry. So what we do is that we solve a minimization problem where the loss function is given by the values of the shape model on the points belonging to this point cloud. So the point is that on the surface, the sign distance function should be equal to 0. So we penalize the output of the shape model. And then we use also a regularization term that consists in the Malanobis distance between the value of the shape code and the empirical distribution of shape codes that we got during the training. And the next feature is that once the inference problem has been solved, then we can evaluate the sign distance function in all the points of the domain, so we can recover the geometry as the zero-level set of the sign distance function, so we can run the marching cubes algorithm to construct meshes that can be used, for instance, in finite element analysis. And these are the reconstruction results. So this is the case without noise. You can see that we can have quite accurate results with an error below 1%, and also the latent shape codes are almost uncorrelated. That means that we found a latent space that doesn't have significant redundancies. What happens instead when we have noise? So when we have noise, we can still have a robust inference of the shape code by framing everything into a Bayesian setting. So suppose that we are given a point cloud, so a collection of points that should belong to the surface plus some measurement error. Then we can interpret our shape model in a generative way. So we can model the probability of observing a given sign distance function in a given coordinate given a shape code as a Gaussian distribution where the mean is given by the output of the shape code and where the standard deviation is associated with measurement noise. Then we have a prior given by the empirical mean and covariance from the training set. And then by the Bayes theorem, the log probability of the log likelihood of having a given shape code given a shape can be written as the sum of the log probability of observing 0 sign distance function at that point, and this is given by the shape model, plus the log probability of the prior, and then a term that does not depend on the shape code. So by taking the maximum of the log likelihood, we end up with this loss function that is exactly the one that we were using before, but where now the coefficients in front of the Malanobis distance has a clear meaning, a clear interpretation, and so we prove that the Malanobis weight need to scale with the noise variance and with number of points. And in this way, we can get a robust inference even in the presence of noise and even with a small number of points. So as you can see that as the noise level increases, or when the number of points decreases, the accuracy gets lower, but still does not increase very much. So we go from 1 millimeter to nearly 2 millimeters. So we can finally design our surrogate model architecture that, as I mentioned, is a neural field where the output is the displacement field, where the inputs are the physical coordinates to which we append the universal ventricular coordinates that allows to provide the positional encoding. So these are coordinate systems quite popular in the field of cardiac modeling. This provides apical basal coordinates, transmural coordinates, and also circumferential coordinates. Then we also append the physical parameters that in this case are the pressure and the stiffness of the tissue. And then we append the shape code that has been decoupled between the size information and the shape information. And for the shape information, we tested and compared two approaches. One is the one based on deep SDF that I just described, and the second is somehow more classical one based on PCA encoding. So we take universal coordinates of a point cloud so that we can take a uniform grid, identical for a geometry, and then we perform PCA and we take the first n principal components. So we applied these methods to our dataset composed of 44 geometries. So we employed 30 for training and the other for validation and for testing. So on the training set, we got an error that was quite good, so below 1%, but on the test set, the error was very large. And so this is a classical case of overfitting because we have a small error on the training set and a large error on the test set. And this means that the model is not able to generalize well to unseen geometries. And so what we feared has become true because we concluded that 44 geometries are simply not enough to learn such a complex problem. And we were a bit disappointed, but we also had some hope because in the end, the shape model was satisfactory in reconstructing the geometries. So we concluded that here the core difficulty was not in learning the shape, but in learning the physical response. And so this observation suggested us to leverage the shape code in a generative way to augment the training dataset to be used by a physical surrogate. So how can we use the shape model in a generative way? Well, the idea is very simple. We randomly sample shape codes by exploiting the empirical distribution of the geometries during the training set. We evaluate them through the shape code and then use the Marchi-Cube algorithm to generate a synthetic cohort of geometries. And by using this synthetic cohort of geometries and by running training simulations that can be used for the training, we can then train again our model by using an augmented dataset, including also 600 generated geometries. And in this way, we can get accurate results also on unseen geometries, so on the testing dataset of geometries that you have never seen before. So in this way, we can get accurate results without overfitting. And remarkably, we were able to do that without introducing any real geometries. We only exploited geometries generated with the shape model. So we exploited the shape model to provide a stronger observational bias to the physical surrogate. And these are examples of displacement fields that we have on top when training on the real geometries only. You can see that the error is almost always larger than 5 millimeters, and instead by augmenting the dataset also with the synthetic geometries, so these generated geometries, we can get much smaller error. The first line is without shape codes. This is with PCA shape codes, and this is with the sign distance function based shape codes. And you can see that in most cases, the errors are below 1 millimeters. So in conclusion, presented using S, that is surrogate models shape informed, that is non-intrusive, it is modular, it allows to change in a modular way the loss function. It's flexible because it accommodates several shape encoding techniques, and I show you at least 4 of them. I've shown that with universal coordinate system we can improve generalization between different geometries. And then I showed 2 learned shape encoding technique, one based on conditional neural ODE, that is good when the topology is preserved, and instead a more flexible one is based on sign distance functions. This is automatic, it is flexible, and it is also accurate. It achieves the same accuracy or comparable accuracy to the situation where we have an explicit parameterization. And finally, in the cardiac modeling test case, I've shown you that in situation of data scarcity, we can leverage a well-trained shape model in a generative way to enrich the observed physical domain and to have a stronger observational bias to improve the generalization capabilities of the surrogate model. And this was done, I say it once more, without introducing new real geometries, but just using a well-trained shape model. And finally, I'd like to spend the last few minutes to answer a question that the organizers asked me, that is the following: where would you like to see your own field in the next 10 years? But first of all, what's my field? So I just one slide to summarize what are my scientific interests. So I'm interested mainly in two fields from the methodological viewpoint. One is the numerical approximation of multiphysics and multi-scale problems, and the second is the synergic integration between machine learning and scientific computing, so scientific machine learning. And then I also have a third interest that is more applied in nature, that is cardiac modeling. And this is the field where I like to apply methods developed belonging to the two field that I mentioned before, which is also a continuous source of motivation for the development of new method. So what's my personal take on the next decade about surrogate modeling, first of all? So I think that the main drawback of surrogate models nowadays is that they lack a well-assessed theory, or at least a theory compared to traditional numerical methods. So what I would like to see in the next years is the development of surrogate models with a certified accuracy. And I think that this can be done either by a posteriori error estimate or by switching to probabilistic neural operators that have confidence intervals inside. Or another way to merge in a synergistic way numerical methods with surrogate models is through multi-fidelity approaches, where surrogate models provide speed up, and instead traditional methods can provide certification of the error. And finally, I hope to see, and I think that there is room to improve existing architecture by injecting more physics inside. So I think that a key to have better generalization is to exploit physics as an inductive bias, so directly into the architecture, rather than as a learning bias, like it is more commonly done today. So what's my personal take instead of about scientific machine learning in general? So first of all, I don't think that neural networks will replace traditional solvers. I think that standard numerical analysis will still be central. And I think and I hope that we will see more and more hybrid methods. So methods that are able to bring together physics first principles with the knowledge contained in large datasets. So exploiting physics as soon as we have physical knowledge, and then exploit machine learning methods to close the model, so to find model closures, or to fill the gap between what we don't know, so what we can model and what we cannot model explicitly. And finally, I think that there is also room for increasing online training, so to develop models that are able to self-adapt as streams of real-time data comes in. So models that are able to adapt to the environment when the new data comes in. Then what about cardiac modeling? There is an ongoing debate about the respective roles of physics and data. And I think that here the main issue is that there is disconnection between the direction taken by mathematical models and the clinical reality. So mathematical models are increasingly biophysically detailed and have an increasing number of parameters that are increasing a higher rate than the data that are available from the clinics, where in many situations we still have a few available data. And the risk is that cardiac digital twins are poorly constrained by the data. And one possible solution might be that of instead of using more physics-based models, then to resort to phenomenological models. But I think that this is not necessarily true. I think that the complexity should be tailored to the specific use case or the clinical question at hand. I think that there are mainly three use cases where we can use cardiac models. One is that of understanding the cardiac function, so studying an abstract or an idealized heart, or for instance, an animal heart. The second is in situ clinical trials, so virtual population of hearts that can be used, for instance, for drug testing. And finally, of course, we have diagnosis and treatment, so patient-specific hearts, the real digital twin. I think that the situation is very different. In the first two cases, we need even more physics. We need more biophysically detailed models, and we need even more integration among the different physics, because the heart function really emerges between the interaction of different physical processes, and there are a lot of regulatory mechanisms that are still not yet well captured by mathematical models. And for these use cases, we really need a mechanistic understanding. Instead, to develop patient-specific digital twins, well, in many cases, a well-designed phenomenological model can be better. Maybe even better could be hybrid models that bridge physics-based components with data-driven components trained on large biobanks. And in any case, we need better algorithms for model personalization. So algorithms that are really tailored to the data that we have in the clinical practice. And finally, what about the research directions that I expect in cardiac modeling? So first of all, we have cardiac electrophysiology. That is, I think, far the most mature subfield in cardiac modeling, also in terms of validation and clinical trials. So the last week, the first clinical trials on the use of computational models to guide ventricular ablation was published by the group of Natalia Trajanova, and I think this was a really milestone for everyone working in this field. And I hope that in the next 10 years, we will finally see successful clinical translation of all the research efforts done by the community in the last decades. Instead, cardiac mechanics, I think, is less developed. There exist models, of course, also advanced models, but validation and personalization is lagging behind, and I really hope to see more mechanics in the next 10 years. And finally, one major obstacle to the clinical translation is the computational cost of computational models. And this is how I open this presentation. And I think that a promising way to address this issue is represented by surrogate models. So with this, thank you very much. Just this final slide, an announcement. I'm hiring, I open positions, both PhD positions and postdoc positions on two different projects. One is related to scientific machine learning, and the other is instead related to cardiac modeling and inference forming. So if interesting, feel free to reach out. I'll be happy to discuss. So thank you very much.
Thank you very much, Francesco. This was a beautiful presentation of very inspiring work. And thanks for sharing your insights also for the future with us. I can remind all listeners that if you will have a question, feel free to write it in the chat and we'll see if we have time. But I have a few things I'd like to start us off with. So when I read your abstract, Francesco, I was very excited to see that you were going to talk about learning across shapes, because I think this is a topic that's very relevant today for many reasons. And I'll get back to that. And then at the beginning of the code, beginning of your talk, I immediately started wondering about these shape codes and how robust your results are to the choice of shape codes. I imagine there's many options, and you touched a bit upon this, but could you say a bit more about more of that?
Yeah, of course, there are many ways of encoding a shape. And so today I mentioned at least 4 of them. One is very traditional, that is taking some landmarks. Another one is also quite old idea, is that of exploiting PCA. And then I show 2 new ideas based on learning a shape code in an automatic way. And I think that yeah, there could be a trade-off between robustness and expressive power. Because maybe the more traditional approaches like the one based on PCA, they are very robust in the sense that also the inference problem is deterministic, is not subject to uncertainty, but on the other hand, the expressive power is somehow limited because they are just so they are limited to represent variations of the shape that are linear in nature. Okay, so that they cannot capture nonlinear variations. Instead, the method that we investigated, that we try to develop, goes in the direction of having methods that are able to handling more flexible kind of variations and even variations in the topology, which in many situations occur in practical situations. For instance, in anatomy, also anatomy is not always topologically equivalent from one patient to the other. Of course, in those cases, robustness is more challenging, and we had to work a lot in that direction. And so we worked a lot in promoting regularity in the latent space, because this is what promotes robustness. So for instance, one example is the one that I showed that is based on using a Lipschitz regularization during training that really promotes a more robust inference. We also tested, so this is something that we didn't mention, we also tested variational approaches based on variational autoencoders, which in some cases can help. And recently we are also testing in a slightly different setting approaches based on meta learning, which can really help in having a very robust inference of shape codes.
Interesting. So one of the reasons I'm asking is because I find that there's now really an explosion in the availability of structural data or anatomical data, at least in the field where I'm working from simulating multiphysics in brain tissue. There's now really an explosion in the imaging data available at the cellular level. But it's very hard to use anything like one specific, I know, atlas or something like that. If you're looking at different parts of brain tissue, it'll be, in some sense, completely different, and in some sense very similar. And there's tons of structural data available, but very little functional data available. So I'd be also interested in seeing these type of techniques used in that type of setting. Do you think there's opportunities for that?
Oh, yeah. I think there is. Clearly, let's put like this: the more complex the shape is, the more challenging everything is. If I think of brains, the presence of sulci, of course, can make things very different. And even though the topology might be preserved, for instance, the number of sulci or the topology or their intersections can make things very challenging. And in particular, I think that in this case, methods based on the formation of a predefined atlas can fail. And so in these cases, we need to resort to methods like the ones that I mentioned, that are based instead of neural fields that are more flexible in representing everything. I'm not expert in brain modeling, but this is what I can expect.
Yeah. So this brings me to this question: how do you choose your
Marie,
Uh,
just real quick, there's two questions from the audience in the chat. Just don't forget about them.
Super, thanks.
Okay, yeah.
I'll finish just this one. So I wanted to ask you about your choice of neural architecture. How do you choose? How do you choose that, and does that make a difference?
Yeah. So for these, so both methods that I presented are based on neural fields, so they are based on continuous representations, and they are both somehow low dimensional in the sense that they are designed in order to have a parsimonious architectures. So we try to use as simple architectures as possible in order to contain the number of trainable parameters, because with a small number of training samples, generalization is challenging if you use a too-rich architecture. So we use the fully connected neural networks. A crucial aspect is the choice of the activation function, because we need a smooth activation function, otherwise the geometry will be not regular. So this is something that we tuned at the beginning. And then we also tested the different activation functions, and we don't have a general recipe for it. We have always based everything of trial and error, and we were surprised to see how sensitive are the results on the choice of the activation functions. And from case to case, we tune automatically, so based on cross-validation, we tune the choice of the activation functions, and it turned out that in some cases the tanh function is better, in some other cases the Selu function is better. So we don't have a generalized, so let's say we don't have idea of why one performs better in one case than the other, but we just go for a trial and error. But if I need to point out one important hyperparameter, yes, one is really the choice of the activation function.
I guess that's something on the wish list for the next decade. Okay, I'm going to ask you two questions from the chat here. The first one is from Hermanegeld Arevalo, you may know. So he's asking about structure beyond shape. So he says, thank you for your talk. And currently the cardiac shape models only take into account overall geometry of the heart. Could you incorporate heterogeneous material properties such as fibrosis into the shape models?
Yeah, that's a very good point. With this, let's say, current state of the architecture, we are not able, because the architecture just take scalar parameters as input, cannot take fields as input, but this is one research direction that we are addressing, and we are doing that by resorting to neural operators, kind of architectures that are able to find maps between infinite dimensional objects like space fields to other infinite dimensional objects.
Super, thank you. Okay, one more from Ricardo Ruiz-Bayer. Great talk, Francesco. Can you comment more on the shape-informed inference carried out for the surrogate training? It seems you do this locally on specific points on the ventricles, giving you heterogeneity information on displacements as well. What other physics can one incorporate in the surrogate training?
Yeah, so let me maybe go back to the to one of the first slides. Okay, yeah. So the training of the surrogate model is done based on a collection of training points. So we have this sum over some points. So what we do is that we collect a large number of points in the ventricle where we know the solution, because this was computed by means of the high fidelity solver. And then we minimize the mismatch between these solutions and the prediction of the neural network on those points. So indeed, here the architecture is a neural field. That is to say, we can query the neural network at any point of interest. So we are not restricted on any mesh-based representation. So what we do is that, so in principle, we query the neural network as many times as the number of training points that we have. Of course, what we do is that we do it in batches. So we collect all the points in a batch, and then we evaluate the neural network. Yeah, to answer your question, yes, we minimize the mismatch on specific points that are basically the points where we have the solutions. So in practice, we take the nodal coordinates of the mesh that we used to generate training data, and we use these points to define our loss function. If the number is very large, then we can do mini batching. And what we typically do, we change different points on different geometries, because in this way we can cover in a more even way the domain, and we don't have any bias towards specific locations, but we can generalize better from one geometry to another.
Thank you. I realize I could have kept this discussion going for much longer, but I would like to ask you one more question, and then I'll send it back to Thomas. So you mentioned that you had, what was it, 44
Yes.
ventricular geometries, right? And I was thinking of, do you have any thoughts on the importance of open data sharing and so on going forward in the field of computational medicine?
You mean if we aim to share our
Is it important that so I think medical clinicians and so on have been reluctant, I think, to share data openly more so than other disciplines because of obvious issues. But do you think this is something that it would be valuable to change going forward, or?
Yeah, so having access to data, as you know, is one of the main challenges when we deal with biomedical applications. And the point is not just having access to the raw data, but it's also about processing them, harmonizing them, and so on and so forth. So here, the challenge that we try to address was to see what we can do with what we could find freely available online. That was really a small number of geometries. Of course, one can think of having access to larger cohorts. However, we wanted to take this as a challenge and to see whether by methodological developments we could be able to find good solutions even in cases with a small number of geometries. Because I think that this is a typical situation that can be also relevant in other cases when we maybe, I don't know, we would like to address a specific pathology. We don't have many patients that is affected with that pathology, so we don't have a large number of training samples. So we really wanted to see whether we can bridge this gap between shape and function by using a shape model. At the same time, we plan to make our shape model public so that people can use it to generate cohorts and use this also for different use cases, because of course the shape is universal. It's not restricted to the cardiac mechanics use case that we investigated, but can be used also for other use cases.
Exactly. That's very true. Okay, thanks again, Francesco. I'll send it back to you, Thomas.
Thank you very much. Thank you for the invitation.
Yes, thank you very much. And thank you, Francesco, once again for this interesting talk. I think I have some technical questions, but rather than sort of continue this here, I'll send them to you via email because I don't think they'll contribute too much to the overall topic. But thank you once again for this lovely presentation. I want to remind everyone who's still with us that next week will be our next instance of the Langtangen seminar. So we hope to see you all there. And this talk will appear on YouTube in case you missed the beginning or something like that. Okay, thank you. Bye, everybody.
Thank you. Bye-bye.